In this video, we're going to examine another bifurcation that has to do with the interaction of a limit cycle and fixed points. So in addition to the Hopf bifurcation that we've already looked at, we have what we call a sniper bifurcation or a saddle node infinite period bifurcation, distinct from the Hopf, but they share the property that they both involve fixed points and a limit cycle. So a sniper bifurcation is basically the study of fixed points on a limit cycle. Okay, so let us consider the example over here. We have a linear term in our differential equation, cubic terms over here, and then we have this nonlinear term that involves the square root of x squared plus y squared, which immediately gives us the hint that it might be simpler to look at these equations in polar coordinates. So let's do that. R is equals to the square root of x squared plus y squared. Theta is the normal angular coordinate. And if we convert them or rewrite the equations in terms of polar coordinates, they simplify beautifully. We have r dot equals to 1 minus r squared times r, and theta dot is equals to omega minus sine of theta. So if we look at just the radial equation, we can plot the 1D phase portrait. So there we have r dot is equals to r minus r cubic, and it has two zeros or two roots, one at r equals to 1 and the other at r equals to 0. We're assuming that r is bigger than 1, so we neglect the root that could also potentially occur at r equals to minus 1. If we want to put this picture onto the xy phase portrait, we see that this a fixed point in the radial coordinate at r equals to 0 immediately translates to a fixed point at the origin. The radial coordinate that has a fixed point at 1, which is a stable fixed point because we approach it from the negative and from the left and from the right, that translates into the fact that as time approaches infinity, the radius will approach 1. Possibly with the exception of the origin. So here we have we call it an invariant curve, a curve that all the trajectories approach. It need not necessarily be a limit cycle, but simply it's a statement that as r approaches infinity, so as time approaches infinity, r approaches 1. And we can see over here that basically means that the vector field points towards the limit cycle at various positions. If we, in addition, assume that omega lies between 0 and 1, we can go and analyze this 1D equation as well for theta, and we can simply plot it, and we have that it's simply a constant, which is in this case assumed to lie between 0 and 1 omega, okay, minus sine theta. So it's a displaced negative sine theta graph that we're looking at. And in the special case where omega is between 0 and 1, this graph has two zeros where theta dot is equals to 0. The smaller one is over here. It's the stable fixed point, and we're going to call it theta star. And the larger 0 is the other unstable fixed point, which occurs at pi minus theta. So if we look now at the Cartesian plot, we have over here theta star, the angle. We have that the radial direction is pointing towards the r equals to 0 circle, and now the arrows in the theta direction also both point towards the fixed point. So it's very definitely a node that's been plotted over here. If we look at the second fixed point, just from our analysis in 1D, we have that it is an unstable fixed point. In other words, arrows leave it. Okay, it occurs at theta, at pi minus theta star, in other words, over here. And it's basically a saddle if we look in the Cartesian coordinates. So in other words, if we put it on this point, here is the pi minus theta star. It's approached in the radial direction, but in the angular direction or the theta dot direction, the arrows depart from that particular fixed point. So it's typically a saddle. What we can do now is examine several trajectories. We can see we always have R increasing and theta going towards the node from the other side as well. So it behaves really like a node. If you're closer to the saddle, it behaves like a saddle. R increases always, but then it departs from the saddle along the theta directions. Similarly on this side, it behaves exactly like a saddle. R increases, but theta, it spins away from the fixed point. And we can continue doing that. And just a few other trajectories also coming in. Now, if omega equals to 1, that's our bifurcation point. Once again, we have this situation for theta dot, just the 1D version or the decoupled equation. We've got theta dot is equals to 1 minus sine theta. So there's only one intersection with the theta dot equals to 0 axis. And we can again translate this into motion in our phase or XY phase plane. Once again, you have this invariant circle of r equals to 1 where the radial coordinate is attracted to, but what happens with the angle is now determined by this plot. So you're going to have this half-stable fixed point that occurs at pi over 2 where the theta dot curve is equals to 0, and we see that for angles less than pi over 2, they're going to increase. They're going to be temporarily stationary at pi over 2, and if they are bigger than pi over 2, they're going to run away. The theta is again going to increase. So if we translate this into our xy plane, for angles less than pi over 2, we're going to increase and approach it from the stable side. For bigger than pi over 2, theta dot is going to increase and go that way around. And we can also go in and put in the arrows for our sniper bifurcation point. And this point at which the transition takes place, where the two saddle nodes, the saddle and the node, in some sense merge and then disappear, is known as the bifurcation point. And here we have those two arrows indicating the direction in which theta is in which theta is going to increase when it gets close to theta star. Okay, once again, the stability is indicated in the radial direction, and then we have the phi dot behavior indicated with cyan colors. If we put in a few trajectories, R always increases, theta increases except at theta equals to pi over 2. In fact, it behaves very much like a saddle on the left-hand side. Okay, so we can get a feel for what the trajectories do look like. Here, if you start with R bigger than that, it decreases, but theta increases until you reach pi over 2, and then continues to increase after a little nudge. Okay, so that's our sniper bifurcation point. If we now continue and we increase omega above 1, we no longer have a fixed point. The fixed point has literally disappeared at the bifurcation point, and we're simply left with this theta dot that is always positive. Okay, so if we plot that, we're once again to have the true case of a limit cycle now. This invariant curve that is always approached at r equals to 1 has no fixed points on it, and the angle simply is positive, so the motion tends to run around the curve. And if we want to put in the arrows, we simply have a situation where the flow is slow over here, where theta dot is close to 0, and then which is basically ghost slow in the sense that the fixed points have disappeared, and then it is faster as you move away from the theta equals to pi over 2 where the bifurcation point was. Okay, and if you put in the trajectories, they look like that. Now, as I've said previously, an important way of identifying a bifurcation is by looking at how the period changes with a parameter, which we're about to explore next. So we're going to try and attempt to get an analytic approximation to the sniper bifurcation It's a limit cycle period. And here are the coordinates again. Here we have the situation after the bifurcation point where omega is bigger than 1, and we know that the flow over here is slow. And just to give you a more of a intuitive feeling for what the flow looks like, what we're now going to do is simply plot various trajectories, and then we're going to show you how each of the x and the y coordinates behave as a function of time independently. Okay, so there's our limit cycle with all our trajectories. Let's now examine how x is a function of time and y is a function of time behave for a specific trajectory. So what I'm going to do is I'm going to take fixed time steps. Okay, so over here, far away from the bifurcation point, the flow is rapid, and so there's a big change in x and a change in y for the given time step. If I take a similarly big time step, you're still going to have a large change in x, larger change in y, because you're far away from where the ghost flow takes place. And you can see by the length of the arrow, the time taken for this arrow and the time taken for that arrow is the same. You now are going to climb onto the limit cycle. You see you're getting closer to where the ghost flow is, and the arrows are getting smaller, but not a lot. And you can see you've also gone past the maximum point over here of x, and you have turned around up at the top here, whereas y is still continuing to increase. Okay, the next little step, your arrows are getting shorter because your flow is getting closer. X has now started decreasing, and y is continuing to increase. Okay, flow gets still slower, but x continues to decrease till you towards the fixed point at, or the ghost of the fixed point at x equals to 0, and y continues to increase, albeit at a slower rate. And so eventually we're going to go and very slowly, exhibiting our ghost flow, approach where the fixed point was. The fixed point is gone because omega is bigger than 0, but the slow is really slow. The flow is really slow, the fixed point. And so to estimate our period, we now want to get basically the time it's going to take for us to go once right around the circle. So let's just put a little marker in over here. This is the point at which we went past the x equals to 0 point, and we now want to estimate literally the time. And you can once again see how the flow is slow up here, and it's going to increase because we're going to take bigger steps with each arrow. We want to estimate the time it's going to take for us to go right round and come back to y. So over here, x is now basically approaching -1, which is its minimum value. It's now going to turn around and start increasing to 1 again. Y, on the other hand, is approaching 0. It's going to continue going negative as we go around the limit cycle, but it's going to do it much more rapidly. Okay, so there we're almost at y equals to -1, and x just past 0. So there we're at y equals to -1, x just past 0. And we're now going to start increasing y and increasing x until x reaches the maximum value, and then we're going to increase y but start decreasing x to 0 until we once again return to the x equals to 0 point from which we started measuring our period. So in order to estimate the period of the sniper bifurcation, we want an estimate of the time it took to go from one orange line to the other orange line. It should be roughly about 8 seconds according to the plot, but we want to see if we can get a formula for it. Okay, so we want to estimate that period t, and this is where the analytics come into a little bit. The period is simply the integral of each little time step around the circle, so we have at least an expression for what we want to compute. Okay, and we know that dt is basically equals to, we can change variables to theta, that we have basically the integral of d theta over d theta dt would be equivalent to the integral of all the little time steps. And we know what theta dot is from our expression for theta dot from the differential equation itself. So we have to work out this integral, and that will give us the period, the time it took to go right round the limit cycle. And so this integral is actually an integral that you tend to learn the first year with a very clever substitution known as the double angle formula, or a lot of people also call it the Weierstrass substitution. So what we're going to do is we're going to set x equals to tan of theta over 2, and then you immediately have that sine theta is going to be equals to 2x over 1 plus x squared, and d theta is going to be equal to 2 times dx over 1 plus x squared. And so you make the substitution. It looks complicated, but if you put it in here, it simplifies it greatly, and you're left with the period being equal to 2 times the integral from minus infinity to infinity of dx over omega times 1 plus x squared minus 2x. The next step is to complete the square in x below the line over here. And the way we complete the square is we identify the coefficient of x squared, and we're going to take it out. So we're going to take omega out over here, and we're left with 2 over omega. And then we want to complete the square with x squared plus 1 minus 2x over omega. And so the way we do that is we have x squared, that's fine. So we want x plus something squared, which is going to be equals to this. We examine the coefficient of x, and we see that it is a minus 2 over omega. And so we subtract minus 1 over omega here, and we square it, and then we add whatever we need back to get this expression at the bottom. So we now have this integral from minus infinity to infinity of dx over x squared minus 1 over omega squared plus 1 minus over omega squared. And then this is a standard integral, and we can do it by simply using what we know. Or if you want to make it clearer, you could replace this by y and then do the integral. But what we get out is that the period is given by 2 over omega squared minus 1 times tan, the inverse tangent of this argument evaluated in minus infinity and infinity. And if we evaluate this at x equals to minus infinity and infinity, we're left with simply that the argument becomes pi or minus pi, or sorry, the argument basically, if the argument is infinity, the arctan is pi, and if it is negative infinity, it is, sorry, if the argument is infinity, the inverse tangent is pi over 2. If it's negative infinity, it's minus pi over 2. And if you add those two, to subtract those from each other, you're left with pi. So the integral evaluates to 2 times the square root of omega squared minus 1. And so we can see we've literally worked out what the period must be if we know what omega is. It's important to notice that as omega approaches 1, in other words, it approaches our bifurcation point, the period approaches something that looks like this. Basically 2 pi over omega minus 1 times omega plus 1. Okay, it's approaching omega from the positive side. So this thing is basically, it's approaching 1 from the positive side. So this thing is basically going to approach 2. And this thing is going to go like omega minus 1. Or we can basically measure the distance of omega from the bifurcation point with mu, and we can show that the thing is equal to 2 times pi over the square root of 2 times the square root of mu, where mu is simply omega minus 1. And so if we go and evaluate it, we can see that if omega equals to 2 minus 1 over the square root of 2. In other words, if it's equals to 1.293, then our period is equals to 2.67, which is the period that we see over here. Okay, so in conclusion, we've basically stated that we can compute the period of the sniper bifurcation's limit cycle analytically in this case, because we can actually integrate over the whole of the limit cycle and simply use our expression for theta dot in terms of omega and theta to do the integral. In other words, we replace t by d theta divided by d theta dt. And so we get an integral we can compute, and through a clever substitution, we get the answer, namely that the period is 2 pi over omega squared minus 1. And this result is true for this specific case. But we will be able to show in general that the period of the limit cycle is entirely dominated by the slow ghost flow near the bifurcation point, and then you can actually show that in general your period for any sniper bifurcation goes like 2 pi over the square root of 2 times the square root of mu. Okay, so this is the way you go about in an experimental environment. If you see a limit cycle being formed with an infinite period, then you can say it is one of two bifurcations, either the sniper bifurcation or the homoclinic bifurcation. However, if you then do a few experiments and you see that as you move away from the bifurcation point, the period changes like 1 over the square root of the distance from the bifurcation point, then you know it is a sniper bifurcation. Thank you very much for your attention. We'll look at the other infinite period bifurcation, namely the homoclinic bifurcation, in a later slide.